So hello everyone. Today I'm going to talk about a data-driven approach to debug info quality. So I'll be talking about the work I did on a Swift compiler earlier this year. So first, a small introduction. My name is Emil Pedersen. I'm a student at Epitech in Paris. I interned at Apple earlier this year, and this presentation is based on work I did while interning there. Where my task was to improve the quality of debug info for optimized code. But I'm speaking personally as a student, and I'm not representing Apple in this talk. So first, why debug optimized code? There are three reasons I can think of. The first is embedded programming. We want to stop using unsafe languages like C in those areas. But unoptimized code is often too big for optimized targets. So we have to use optimized builds even when debugging. The second is crash logs. When we receive those, we still want to be able to debug what happened on a production build. And the third one is complex programs. Debugging in unoptimized compiler gets really slow, so I would often prefer debugging the optimized build to go faster. The problem is that debugging optimized code is unreliable. Stepping is not perfect. Variables are often unavailable. And in Swift, sometimes the variables just don't exist. When debugging C++, I often have to go up or down a few frames before I see the value of my variables. So the information is there somewhere in the compiler, but why can't we keep track of it? I believe that variables being unavailable is preventable in many cases, and we can fix those cases. So why does it happen? First, let's take a look at the Swift compiler pipeline. Swift code goes through the AST, where macros will modify it and can change debug info. Then it will go through the Swift intermediate language, or SIL, where optimization passes modify it, and then through LLVM IR with its passes, and through machine IR with its passes, before getting to the object file. And the debug info representation is different for each stage. So when lowering to the next stage, we can lose debug information, and at each transformation within stages, like optimization passes, we can lose debug information. So variables can be lost while translating from one stage to the next, but most of the time they are dropped because optimization passes are written to optimize code and aren't designed with debug information in mind. In Swift, passes often completely remove debug variables, so they don't even show as unavailable in LLDB, they just completely disappear. And today we'll focus on how we can improve optimization passes. A first simple approach is to read the code and try to understand what happens, but good luck with that. A better approach is to use a known example of variables being dropped by the compiler and then bisecting to find where it's lost, like at which pass. A way to do that is to use Dexter. It can help bisecting LLVM passes, but it requires a code sample with a known debugging problem, because we have to tell it what to expect. And so that only works for LLVM and not SIL. It also runs the whole pipeline, which can be slow. So the solution I'm presenting today is variable drop statistics. So what is it? Those statistics happen within the optimization pipeline, so within one stage. Today I'll take the SIL stage as an example, but it would be the same for any of the stages that have optimization passes. Within the SIL optimizer, there is a lot of passes that will each modify the SIL code. Variable drop statistics work by running statistics between each pass. When statistics are gathered, we will get a list of variables defined within each function. Then, for each pass, we compare the before and after, and if there is a difference, that means a variable was dropped by the pass, and we report it. If a variable was added by a pass, which happens when inlining code, that's normal. But once a variable was added, another later pass shouldn't remove it again. What constitutes a variable? Two variables are considered the same, so in the before and after, if they have the same name, the same scope within the function, which includes which function it was inlined from, and the same source location. So two identical variables can appear within the same function at the same time. That happens when a variable got split into different allocations by SROA, or when a value was modified. And we don't track those fragments, we just track if the variables still exist. And for Swift, we can run the compiler with those statistics enabled on any code base. We can run them on the Swift standard library because it has an impact on all the Swift code that we write. But the problem is that it's a bit special and it's not really a representative of code that can be written by developers using Swift. So we can run those statistics on the whole source compatibility test suite, which is comprised of over 200 open source Swift projects. So that should be representative of what developers usually do. So if we run our statistics on the source compatibility test suite, we get those big numbers. About 2.7 million variables are dropped in total by different passes. The passes dropping most debug variables are those passes that have a lot of different heuristics, like simplify CFG or still combine. That makes sense. But we can also see SROA up there, which is a pretty simple pass that really shouldn't drop debug info. Some variables are okay to drop. When a function is unreachable, such as with dead function elimination or a dead code elimination, it's okay to remove the variable. Same thing when a scope within a function becomes unreachable, which means that the scope would be visible on none of the instructions on which I could set a breakpoint, then dropping the variable is fine. Also, the standard library defines transparent functions, which means we don't allow stepping into them, so those variables can be deleted too. So the variables will not appear in the debugger in this case. Some variable values should be dropped when a variable is unused or when its computation is moved into a new scope. Then it can be unavailable in the original scope. So if we can't keep track of the variable, it must not be removed. It must be marked as unavailable at that location. But this is often not done well by SIL passes, which is why variables disappear so often. Simplify CFG is one of those cases. If a value is folded and can be calculated by dwarf expressions from available values, then we should also show them as unavailable while keeping the variable there. But some passes should definitely not drop debug value for variables. When a variable is split into multiple allocations, like with SROA, or when it is moved from an allocation to a register with mem2reg, or when it is moved from the heap to the stack with allocbox to stack, the debug value should follow. When a constant is folded and can be represented as a constant in a dwarf expression, then we should do so. And all of those passes were losing debug information at the SIL level. The problem is that these passes here in orange are mandatory passes in the SIL optimizer. They are also run when compiling at 0. So that's not good. If we run the compiler in debug mode with variable drop statistics on, we can see that regular variables are dropped when compiling for debugging. And because of some logic errors, some variables were showing up in the wrong scope, and they would be unavailable in the original scopes. And sometimes they would be dropped because they weren't handled. After fixing those issues, that's what it looks like now. Most passes are completely fixed, and 2/3 of cases with loadable by address are fixed. The ones in blue were from transparent functions, so that's fine. Now, how did I find the real issues? Like, I only have numbers here, not examples that can help me find mistakes. The statistics report has more information than just the total number of dropped variables for each pass. It will also include the name of the function in which a variable was dropped and the pass number. We can then recompile the part where the mistake occurs with flags to look at the SIL on a small function before and after a faulty pass, and it is actually pretty easy to understand what happens once we have that example. So if you remember, that's what the report looked like for optimized code after investigating issues and fixing them. That's what it looks like now. Simplify CFG is now dropping 12% more variables because they aren't dropped by earlier passes, but overall we're dropping 35% less variables, from 2.7 million in total to 1.8 million. Passes such as SROA and fee expansion that should have never dropped variables are now fixed. Now the current 8 passes dropping most debug variables are those, and we should focus on those passes to have the most impact on debugging optimized Swift code. So if you're interested, the pull request for the variable drop statistics can be found here. There is one PR for Swift, and it has recently been ported to LLVM IR, so we can also fix issues in LLVM IR optimization passes. So there is still a lot to do. The LLVM IR patch was merged recently, and we could also add similar patches to different stages, such as machine IR. But we could also add them between stages, like from SIL to LLVM IR, or from LLVM IR to machine IR. And we have a few passes that do a lot of different things, such as inst combine in LLVM and SIL combine in SIL. And it can be hard to know what subpart is responsible for variable being dropped, so it would be nice to have more fine-grained statistics. And we would also like to automatically determine if variables are being dropped for a good reason or for no valid reason, and have separate numbers in the report. Thank you for listening.